So to start, I have a few questions for you all, just because I have no idea, like, who you are really. So how many of you would identify as like a statistician? Okay, you don't have to feel ashamed. What about as a data scientist? Okay, interesting. And what are other people? What are other common, like physicists? A few physicists. Biologists? Okay, cool. You're like segregated. You've self-segregated yourselves. Anything else? Geoinformatics? Economists? Okay. And how many of you use R currently? Okay. And what about Python? Okay. And what about SAS? Okay. And MATLAB? MATLAB users here? Okay, no MATLAB users. What about Excel? And no one's got to admit to using Excel. I'll just assume you all do. Okay. Okay, that's helpful. So today I'm going to kind of talk a little bit about how I think about data science. I think sort of your obligation whenever you talk about data science to define what you mean by data science. So I will talk a little bit about what I mean by data science, and then talk a little bit about sort of why I think like programming data science in particular is so important. So to talk about data science, I'd like to first talk about data analysis, because to me, data analysis is the process by which kind of raw data comes in one end and understanding and insights, knowledge come out the other. And I'm primarily a tool builder, so I think about data analysis through the tools you use to do it. And the first thing you need to do if you're going to do data analysis is you need to import the data into whatever computational system you're going to use. So I'm going to, I use R basically exclusively. So I'm going to talk about R, but I think all of these ideas apply like regardless of the computational tool you use. You always have to first start by importing it, whether it's Excel spreadsheets, CSV files, as a database, an API. You've got to get to the data wherever it lives and get it to you so that you can start to play with it. Then I think it's a really good practice to tidy your data, by which I basically mean like storing it in a consistent way. Basically, every variable should be in a column and every column should be a variable. If you do this or you store your data in some consistent way, your life is going to be much, much easier when you start to do the other parts of the analysis. So once you've got your data in, you've got it into some kind of consistent form that you can actually work with. And this is not, I don't mean by tidy, I don't mean clean, right? If your data is clean, you're, I think, reasonably certain that it's correct. When your data is tidy, it's just in the right shape to make the rest of the analysis easier. Once you've done that, you're going to want to understand your data. And I think there's three main tools to do that. So first of all, you'll often start off with some basic transformations. Maybe if you're dealing with a very large data set, the first thing you'll do is just a bunch of counting. Like, I think counting is one of the most powerful tools for big data. Or you might create new variables from variables that already exist in the data set. You might re-express the data in a way that makes a little bit more sense for your problem. But then to me, there really are two main engines of knowledge generation: visualization and modeling. And visualization is fundamentally a human activity. So you are going to look at the data, and that's going to help you do two things primarily. First of all, it is going to help you take those vague, ill-defined questions you have inside your head and make them more precise so that you can actually answer them quantitatively. The other thing that looking at your data is going to do, hopefully, is surprise you. You're going to see something that you did not expect. And that, I think, is really, really valuable. That's where, like, kind of scientific discoveries happen, when you look at a plot of your data and you see something that is genuinely surprising. Now, like, I don't know, 95% of the time, that surprise is going to turn out to be a data quality problem, I think. And my rule of thumb is if you do, like if your first visualization does not reveal a data quality problem, it's simply that there's a data quality problem that is not yet revealed. But visualization, because it is primarily a human activity, has some limitations, right? As the number of variables gets bigger, as the number of observations get bigger, you cannot look at every possible visualization. And so to me, the complementary tool of visualization is modeling. And I think of modeling very, very broadly. This is like statistics, machine learning, deep learning, like whatever. But basically, whenever you can make a question precise enough to answer with an algorithm or some summary statistics, I think of this as a model. And models are fundamentally computational, which means that they scale much, much, much better. And even if they don't scale particularly well, it's much easier to buy more computers than it is to buy more brains, right? And certainly much less messy. But every model makes some assumptions, and a model by its very nature cannot question those assumptions. So in some sense, that means a model cannot surprise you. So I think this is what makes modeling and visualization so powerful and complementary. A visualization can surprise you, but it can't scale. A model can scale, but it can't fundamentally surprise you. So in any real analysis, I think you're going to circle through these steps again and again and again. You might start with a scatter plot. That scatter plot suggests a linear model. You transform your data to look at the residuals. You visualize it again and again and again and again. And at some point, you're going to decide that you're done. That hopefully this isn't because you've like tortured the data until it's confessed to something. Hopefully this is because you've now kind of reached you feel like you've extracted all the insights, you've got to the end of your pre-registered study, and now you need to do one of two things. So I think kind of traditionally, like this is sort of my background on statistics, traditionally what you'll do once you've done with the analysis is you'll communicate that to someone else. You will create a report, you'll create some visualizations tailored for communication that help other people understand exactly what it is that the data is telling you. I think the other thing that's now becoming increasingly important, and is one of the places that kind of statistics and data science differ a little bit, is that often you will not create something that is aimed at other humans, but you'll automate to create some product that is now ingested by other algorithms. So maybe you're going to create a process whereby new data comes in every day and it gets automatically classified. So I think these are the main two endpoints, right? Either you create a report or a presentation or some kind of interactive app that other humans are going to look at that's going to convince them of the correctness of your analysis, or you're going to automate that analysis so it can be done day after day after day as new data comes in. So this is data analysis. What is data science? Well, my kind of definition is it's just data analysis plus programming. So I strongly believe that if you are not programming, you are not doing data science. You are doing data analysis, which is a really, intellectually rich and important activity. But the key thing I think that distinguishes data analysis from data science is programming. So we can kind of like amend this diagram with another label, which is program. But really, it's not this sort of separate activity. It's something that like underlies absolutely, well, I guess it doesn't really underlie the communicate part so much, but it underlies pretty much everything else you are doing, right? Because to express your ideas, your questions, the way you're attempting to answer those questions, I think you should be expressing those ideas through code. And a lot of what I have worked on is this collection of packages called the tidyverse. And basically the idea of the tidyverse is to kind of pair each of these tasks with packages that allow you to express solutions naturally. And I think a lot of the benefit of the tidyverse is this sort of this idea of notation. Like often when you're solving a mathematical problem, right, 90% of the challenge of solving the problem is simply finding the right notation. Like once you've found the right notation to describe your problem, or if you've found the right notation, you'll often discover the solution is relatively easy. And so what I spend a lot of my time thinking about is kind of what is the right notation for data science? How can I help you express your problems, your questions of the data in such a way that the answers, that you can answer those things fairly simply. And so what I want to talk about today is like, why do I believe that like coding is so important? Like so important that if you're not coding, I would claim you're not doing data science. And I think, you know, the disadvantages of code are obvious, right? Like when you open up RStudio, like this is what you see, right? There's just a blinking cursor staring you in the face. Like it's not suggesting anything, right? At the same time, it's not preventing you from doing anything. You can do anything you can imagine, but that's also a big challenge, right? Because anything is sort of equally easy means like anything is equally hard. And so I think it's like very easy to see why programming is like hard. So what I want to talk about is like, why do I think it's really important? And there are three main reasons. So code is text, code is readable, by which I mean it is able to be read, and it also finally, which is particularly important for science, I think it's reproducible. So I think the fact that code is just text is really important, and it's surprisingly easy to miss this benefit. But I think it's really important because it gives you a couple of really powerful programming tools. And the first programming tool is copy and paste. Right? You've managed to solve one problem, and so you copy and paste that code and you modify it so you can solve another problem. Now, I'm not recommending like this is where you should end your programming journey, but this is a really good place to start. Right? Copy and paste is a really powerful tool for like doing the same thing again with variations. There's another really important variation on this technique, which is you copy your error message, you paste it into Google, you find the Stack Overflow page, and then you copy the answer and you paste it back into your R session. And again, I'm not saying this is where you should like end your programming journey, but I think this is a really, really important skill, right? Because code is just text, you can copy it, you can put it into Google, you can put it into Stack Overflow, you can put it in an email and ask someone for help. And that is really, really valuable. Like when you compare this to using some kind of point and click interface, like if you're having problems with a point and click interface, how do you describe what your problem is in a way that other people can find out about it? The next really important part of code is that it's readable in the sense that you can actually, like someone else can look at it and hopefully gain insight from it. And this for me is kind of one of the scariest in the few times where I do use Excel. This is like the scariest dialogue because I've selected a column and I've clicked sort. And Excel, helpfully now, this is a relatively recent innovation. It says, do you want to expand the selection, i.e., do you want to sort this entire table, or do you just want to sort this one column? Right? You never just want to sort that one column, right? Because that effectively like randomizes your data. And the fact that that's not even the scary thing, right? The scary thing is if you do that, there's no record of it. And this to me is like the scariest thing in Excel, that there's no provenance. You have no way of telling how do they go from my input data to this result. Whereas when you have code, you can actually read what someone has done and think critically about it and say, like, is this the right thing to have done? And I think this is important, like, for your own code, and thinking about code as a medium of communication is really important, because you're always engaged in collaboration, right? Often that even if there's no one else, there's always future you, right? You're always collaborating on your code with the future version of you, and the past version of you does not respond to emails. So, like, they're the worst possible collaborator. So thinking about, like, how, like, not just code that solves the problem, but code that kind of clearly expresses what it's doing in such a way that other people, including future you, can read it and understand it, I think is really, really important. And you don't get that, you do not get that for free, right? You cannot get that just by looking at the sequence of steps that you've taken. If you inspect your R history, you cannot get that. The only way you can get this is by, like, the only way you get good writing, which is by rewriting. So you have to first solve the problem using code, and then you have to rewrite and rewrite and rewrite until it is actually clear what you are doing. Now, it's not always important to do that. Like, there are a lot of kind of low-stakes situations where if you can't understand your code in 3 weeks' time, it doesn't really happen. It doesn't really matter. Although in my experience, every time I've been like, I'm going to use this code once and I will never look at it ever again, I always have to look at it again, and then I have no idea what I was doing, and it's, if anything, harder than doing it from scratch. And I think the last really important thing about code is, because you have captured what you are doing in a way that can easily be rerun, your analysis is now reproducible. So that if the data changes, you can easily rerun all of your code and get the same results out. Now, maybe what the data is telling you is going to change, but typically what's happened is you've just got some small update. Maybe the data has changed. Maybe your collaborator has discovered some new data at the bottom of their file drawer. But having that ability to rerun exactly what you've done is really, really important. And I think one really important tool to do that is R Markdown. How many of you have used R Markdown before? Okay, so R Markdown, a really amazing tool. Basically what it allows you to do is mingle prose and code together, and then you run that code and insert the results of that code with your prose, and then you can then turn that into some format that you can share with other humans, whether that's HTML or a Word document or a presentation or a LaTeX file or a PDF. It doesn't really matter. R Markdown allows you to kind of ignore that, like, what is the final output going to be, and write in a plain text format that, again, it's just text. You can put it in an email. You can share it with others. You can use it with tools from software development like Git or Subversion, tools that allow you to track the changes over time. Really, really powerful tool set. And now I have this slide, which I don't recall what this has to do with. Oh, okay. And this isn't. So another kind of aspect of reproducibility is doing the same thing to different data sets. And I think one of the neat things about kind of thinking programmatically is, like, what is a visualization? You can think about a visualization as just a mapping between a data set and a plot, right? And you can think of it as a function in this sort of mathematical sense, that data goes in one side, a visualization comes out the other side. And now you can start to think, well, what if I've got a bunch of data sets? And I've just kind of stored them in a list. This is the R data structure, which allows you to store multiple things. It doesn't really matter. But now you get access to these tools from functional programming where you can say, take each of these many data sets and this function that turns a data set into a plot, and now you can produce many plots with a single line of code. And the same thing kind of applies to, like, R Markdown reports, that you can think about now, like, an R Markdown document is almost like a function that takes a data set and produces a report. This isn't typically how you think about it when you're thinking about a scientific article, but there are lots of other cases where you're thinking about, well, I want to generate like a report about the grades of every student in my class. And having this capability to generate not just a single document, but one document for each of the many sub-data sets I have is a really, really powerful and useful idea. But you might kind of wonder, well, if data science has to be done by programmers, there just aren't that many programmers, right? So what about all of the people who don't program? And I think here it's really important to make the distinction between kind of being a programmer and programming. And because most people are never going to become a programmer, but they might do some programming to make their lives a little bit easier. And I think the most important takeaway is that you don't need to be a programmer to code. You can be like an amateur coder, or you can be an armchair coder. Like, you don't need to devote your entire life to programming in order to do something useful with it. And so to kind of walk you through that, I'm going to take this visualization. How many of you have seen this before? Okay, well, it's surprisingly few. Yeah, so this is the Gapminder data set made famous by Hans Rosling. If you've never seen Hans Rosling present this data, I would highly recommend watching a video of him, because he is so much better at presenting this data than I am. He is a wonderful, wonderful presenter. But basically, each of these dots is a country. We have got income on the x-axis, or GDP on the x-axis, and we've got life expectancy on the y-axis. And so what I want you to think about, I'm going to give you a little challenge. What I want you to think about is, if you were going to recreate this plot, what's data? I want you to imagine in your head, what does the data set look like behind this plot? And in particular, like, what variables do we need and what observations do we need? So I want you to turn to your neighbor, talk this over. You've got 1 minute to figure out what data you'd need. So hopefully you should have very strong opinions about what this data should look like. And so when you imagine this data set in your head, like, what's one column that's going to be in this data set? The continents, right, which are encoded in color here. What else? We need like the income, or the GDP, and the life expectancy. We need the year, which you cannot actually see here, but it's actually in the background. There's 2015 written in pale gray, which does not show on this projector. But yes, this is a particular year and time. Population, because that's what the size of the dots represents. And the name of the country, right? So we need, I think, these 6 variables. And I'm going to put each country in a row, each country for each year in a row. Is this how many of you imagined a data set that looked kind of like this? Okay, interesting. And so once you've got your data in this form, now how do you turn this into a visualization? And here I want to talk a little bit about the code that you might, or one of the steps you might use to do this in R using the tidyverse, because I think, like, basically the sort of the phonics here are really important. Like, I don't know if you have this discussion in Europe. You probably don't, because your education system is reasonable. But in the US, like, there's this big discussion, like, when you're learning to read, how should you learn to read? Like, should you learn to read by pronouncing, like, each individual letter? And then you kind of combine those pronunciations to make a word, which, as I think about it, probably works better in every other language apart from English. So probably, but there's sort of recently this school of thought that you kind of teach like whole words at once, and this has been very popular in the US, basically not very good. But the basic idea is, like, I think when you're first learning to code, the number one thing you need to learn is how to read code in your head. Like the phonics, being able to read this in your head is really, really important for understanding code. And this looks a little bit cryptic at first. There's a few weird symbols here, but if you can learn how to pronounce those in your head, it's going to make this less forgiving. And so when I read this in my head, I say, take the gapminder data, then filter it to find all of the rows where the year equals 2015. And then I pronounce this thing as creating this new variable gapminder 15. And so what we're doing here is creating a subset of this data which just has the data for this year, 2015. And this symbol, this is called the pipe. I am pronouncing it as then because you use it to combine multiple sequences of steps. And this is the right assignment arrow in R, which until very recently I thought was an abomination that should never be used. But I have basically been convinced by this like phonics argument, because you can read this as a sentence, right? Take the gapminder data, then filter it, creating a new variable called this. And I think that like when you're learning to code, this is like the most important thing. And I think like code like this, like there's some new syntax there, there's some new grammar there, but you can learn to write code like this in a couple of hours. Particularly when you have this kind of this anchoring, this ability to read it in your head. So now that we've got that data, let's turn it into a visualization. So we take the gapminder 15 data, then we're going to feed it into ggplot. We're going to plot it. And when we create a plot, what you need to specify is how do you map the variables in the data set to things that you can perceive. And so by convention, this is the thing on the x-axis, this is the income, this is the thing on the y-axis, the life expectancy. And so now you will notice this plot is blank, which is not terribly useful, although we do have the scales. The other thing we have to say is how are we going to represent each observation? And we're going to represent each observation with a point. And to be more precise, the geometric object we're going to use, or geom for short, is the point geom. And so this is going to give us a scatter plot. So obviously when you when you want to express your ideas in code, you're going to have to learn some kind of new vocabulary, right? You're going to have to learn a little bit of jargon. And jargon is like obviously, like it has its pluses and minuses, right? Because when you start talking in jargon, only people in your discipline are going to understand you. But at the same time, that jargon allows you to very concisely express complex meanings. So here we're saying geom point, you are going to learn that is a geometric object, and so we're going to get a scatter plot. If we compare this to the original plot that I'm trying to copy, can you spot the difference? There's quite a few differences, obviously. But the scales are different, right? If we kind of zoom in here and look at this, you'll notice this is on a log scale, right? Each unit represents a doubling. It's a multiplicative increase rather than additive increase. And so if we want to express that in ggplot2, now we're going to add on a scale where we say we want the x scale to be on the log 10 scale. And now you might say, well, we want to add some additional aesthetics. We also want to map the color of the plots to the region of the world that they come from, which is roughly the continents. With the kind of, well, there's a complicated question of whether Australia is a continent or not. And then there's then the rest of the bits around Australia, like New Zealand, I think here just gets lumped. Actually, I'm not sure where that gets. I guess that all gets lumped into Asia. So these aren't really continents, but they're kind of useful groupings of the world. And we could say, well, what about the population? We want to map that to the size of the points. And so I think anyone can learn to code at kind of this level because you're just describing what you want the plot to do. We're saying we're going to take a data set, that's what we want to visualize. We're going to put income on the x-axis, life expectancy on the y-axis. We're going to map the color of the points to the 4 regions variables, the size of the points to the population, and then we're going to use a log scale on the x-axis. But there's some things that are really challenging to express this way, right? So here I have another plot. So like this is really easy, right? I think anyone, you could, I am reasonably certain that anyone can learn to write code like this in like 2 hours. And I think there's like evidence to suggest that like people are teaching kind of this level of code to high school students now, and they can use it and they can enjoy learning it and can remember it and do it again after the fact. But there are some things that are like really hard to express like this. So here's another visualization. This is a visualization of some cars. So on the x-axis is the displacement, the engine size, and on the y-axis is the fuel economy. So this is the number of miles per gallon, which is like the reciprocal of the fuel consumption, which is what you use in Europe, which is more sensible because generally you drive for a fixed distance. Like you want to know if I drive 100 kilometers, how much fuel will I use? You don't want to know if I have 1 gallon of gas, how many miles I will get. But if we look at this, you might say, well, these points are interesting, right? There seems to be like a fairly strong relationship. But there's these points that are a little bit unusual. And I can like circle these trivially, right? I'm doing that now. But how would I express in code what those points are? That's something quite challenging to do, right? Like I would have to maybe like say, well, the greater than 5 displacement and the highway is greater than 20. Like it's a little fiddly to carve this off, and you can imagine if you've got like unusual points somewhere in the middle of the data, that's really hard to express. And there are some other things that you often have to do when you're doing an analysis where you often like, you load some data in and the data has spaces in the variable names, which is always like a nightmare to work with. And so you want to rename them to like succinct names that have spaces. And writing out code like this, and this is just the dplyr code that rename, so probably we could make this a little bit more expressive and call this rename so it's more clear what it's doing. Like to create this, there's a kind of a bunch of like copying and pasting and retyping variables that already exists. It would kind of be nice if there's like some way to help us do that. And so one thing I think ideally like the primary interface to doing data science should be code because it has these really big advantages. But there are some problems that just don't really allow that kind of precision. It would be nice if we had some tools to kind of generate the code for us. And I think this is a really, really interesting area of kind of work and of research that now you can actually create little interactive widgets in RStudio where you can select those points, click a button, and then it will generate the code that will select those points for you. So I really believe that like the primary interface should be code. And most of the time, you should be typing that code, but there are some tasks that just typing code is annoying, and it would be nice to have some little add-ins that help you do that. I think there's sort of other interesting questions you can start to ask. Like when you're expressing a data analysis with code, I think a really interesting framing is to start to think of that code as data. And when you start thinking about that code as data, like you've written a few steps in a pipeline, be kind of really interesting problem to like, can you predict what is going to come next? Like, can you guess, like, based on what other people have done in the past, can you kind of predict, like, the 5 most common next verbs? And I think this idea of thinking about, like, autocomplete and how can we kind of guide you along the successful path is really, really important. And, like, there's a little bit of this in RStudio, like, when you type library, it's going to list all of the names of packages, because that's obvious. That you want to load a package, but it's cool to think about, like, if we see that you've already loaded 3 other packages, can we suggest, like, can we prioritize this list in some way to suggest the packages that other people, you know, what other packages do people who've purchased these other 3 packages want to purchase? And then there's some even, like, cooler things, like if you've ever written regular expressions, like regular expressions are kind of this incredibly concise, almost like mystical language that allows you to do like really useful string processing stuff. There's a bunch of interesting work in computer science about, rather than you typing the regular expressions, can you provide a bunch of positive and negative examples and the computer generates the regular expression for you. Or if you want to keep going kind of even crazier, there's this neat service where you can take a picture of an equation, and here these are all tattoos, and does some machine learning and like generates the LaTeX behind that expression, which I think is really cool. I don't think that's particularly useful, obviously, unless you have like a lot of tattooed formulas prearranged for this. So I think like I simultaneously really strongly believe that like code is really, really important. And I spend a lot of my time thinking about how can we make coding as accessible as possible? How can we make data science as accessible as possible to people who can't code? But at the same time, sort of think about like, hey, well, what are other interfaces that where code is kind of what we produce, like we're not typing the code in, but can we have other tools that create the code for us? And I think there's a lot of really interesting creative ideas that are yet to be explored. So I kind of want to finish off with this quote from John Chambers when he was thinking about S, which is the system that led to R. That I think is really, he wrote this in like the early 80s, I think, which is incredibly prescient. That like the goal of S is to give you this interactive environment where you can do data science, where you can do statistics, where you can do data analysis, and you are programming, but you're not thinking about that. You're not thinking of yourself as a programmer, but it is a programming environment so that as your needs get more sophisticated, you can just kind of gradually like slide down the slope until you're actually doing programming. And not everyone has to go down that slope to the same extent, but having that ability, like you can start with these very simple ideas. You can start with templates where you just copy and paste and modify, but that's not where you're stuck. You can get more and more sophisticated over time as you need it. And the way I kind of think about this is like the pit of success. Like my job is to dig a pit of success. And a pit of success is very different from a peak of success, right? Or a pinnacle of success. Because to get to a pinnacle, you have to strive. You have to work really hard to get to the top of the mountain. The idea of the pit of success is you kind of like fall into it without even trying. And I certainly don't want to claim like that's where R is today. Maybe it's more like a pothole of success that you sort of like trip over and fall in a little bit. But to me, like this is like really important to me, like particularly like as the world needs more and more people with the ability to take data and to turn it into knowledge and insights and understanding, like how can we give those people the tools, the programming tools, where the path of least resistance kind of naturally, as much as possible, leads you towards success. And so I'm going to quickly realize I have the wrong version of that slide. So I'm going to quickly edit my presentation and give you the correct final slide, which is this. So and this is the goal of the Tidyverse, which is the collection of packages here, is very much to dig that pit of success. If you want to learn about more about these tools, I just kind of glanced over them very quickly today. There's a website, there's a book that Garrett and I wrote about that basically if you want to learn how to do data science, you've never programmed before, this is kind of our best attempt at helping you become like a reasonably competent data scientist with as little pain as possible. There's still going to be some pain, I'm not going to lie, but it's the smallest amount of like necessary pain as possible. Thank you.
Okay, thank you very much. I'm sure there are many questions. I'm going to hand this object around for the questions. As you've noticed, it doesn't sound like a microphone, but we need it for the live streaming. So, are there any questions?
Thank you. Thanks a lot for your very interesting presentation. I enjoyed it a lot. So, I have a question regarding the way how to approach new programming problems. So, I find myself stuck in quite some cognitive friction by pulling together all the different pieces which are related to the new problem I want to address. And what I think would be really cool, just as you said, as I type, having suggestions, for instance, like in Google or in WhatsApp. Yeah. So when will you deliver this to us?
Honestly, I will probably never deliver that, but hopefully someone else will. One of the other things that I think is really important with programming, and the thing that I think makes me kind of a better programmer than ever, like the thing I think you should optimize for when you're learning to program is basically making mistakes. Like there is no way to create a good visualization without creating many bad visualizations. There's no way to write good code without writing a lot of bad code first. And so I think one of the things that you should consciously think about is how can you write bad code as quickly as possible. Don't think about like how can I write good code. Think about how can I write bad code as quickly as possible, because I think if there's one thing I am really good at, it is writing bad code very, very quickly. And that is a really important skill because I can start by quickly doing something that is bad, getting some insight from that and doing a little bit better, like figuring out how to build that loop of iteration. I think that's one of the ways that kind of helps me get unstuck. Like there are so many things you could do in the next step. Like just do one and do it wrongly as quickly as possible.
Can I quickly follow up on this? You keep track of the others. Right, so and that brings me exactly to my next question, and the struggle I face is essentially, so when I do this, so I do a lot of messy coding, then it's even harder for me to find the bits and pieces which were useful, right? And then to filter and find out which pieces of code might be more useful in the future or less useful in the future is quite a thing. So I don't have a real system of handling this, which always, and that's the main point, exposes me to this cognitive friction at the beginning of sorting out which pieces are necessary. And is there any let's say daily practical advice you can give to me?
I think the thing you have to do is like once you have solved a problem, like once you have code that works, you have to rewrite it to be clearer and easier to understand. Like this is the same way like you write prose. Like the way you write a paper is by writing a bunch of like bad sentences that are hard for people to understand and then by rewriting them. Well, that's certainly the way that I write a paper, and if you have better techniques, if you can just simply write the correct sentence first, you're extremely lucky. But I think it's the same with code. You just have to rewrite, and that gives you like the practice kind of like honing in on what's the important parts of your code. And over time, like you will just get better at writing like the correct code the first time. But I think there's no way to do it.
That's not the answer I wanted to hear. Okay. But, okay, thanks.
So obviously a problem with code is when you make a mistake and you introduce some artifact into your data that you're not aware of and you miss it. And sometimes you come across it just by chance and then you think, oh, what about it? What are all these mistakes that I'm making that I'm not coming across by chance? Is there anything moving in the direction of like the grammar check in Word where you sort of look through someone's code and say, looks like you maybe wanted to do something else?
I'm not aware of anything, but I think that would be like fascinating to pursue. I think that the problem is like, how do you end up like getting that in exactly the right place is really hard. Where like the grammar check, I think for a long time has been kind of like hit or miss. And you certainly don't want to end up in like the Clippy situation where it's like, you know, I think you're trying to do a linear model. Like, you want to do this. So I think that kind of like sort of intelligent help is really, really, really hard to do. And so I think for now, like I think the right thing to pursue is kind of like checklists. Like when you do an analysis, like you should be able to think like someone should write a checklist, which is like, have you looked at a histogram of every one of your continuous variables? Have you looked at the distribution, the univariate distribution of every single variable in your data set? And if you have not done that, that is like, you know, something you should fix. So I think that idea of having these sort of like pre-flight checklists, these are the things that you should have done is really valuable. I think the other thing that seems like an interesting thing to pursue is again this sort of idea of like code as data. And if you think about like your code as data, like can you visualize the code that you've used, and can you kind of use that to say, well, like what parts of my data have I actually looked at, and more importantly, what parts have I not looked at and I should do next? I think that's a really, really challenging problem that someone should work on. But again, it's probably not going to be me.
Okay.
Yeah, hi. So thanks again for the talk. Very nice. I first want to comment on the first two questions and then ask my own question with respect to that. So Hadley already said it correctly. I think these are intelligent tasks, so the best way to solve it is not by computer or on your own, but by another human being. So my idea would be maybe get somebody to talk to, explain to him what you want to do, what your code is, and then often just restraining yourself to using words rather than your thoughts often sorts things out. If there's nobody around, think about getting a supervisor. If that's not easy to do, get a rubber duck. I'm serious. Get a rubber duck. Explain to this duck this. Yeah, thank you. Perfect. So rubber duck debugging, it's a thing. So my question for you would be, I've heard that in companies or in general, good programming people often do this paired programming, two people in front of a computer. How is it at RStudio, or how's your experience with it? Is that something you think is useful? It should be done always, should be done sometimes, and so forth?
So we basically never do pair programming, and so therefore, since we don't do it, like it's obviously not useful. That I don't know. I think like the challenge of pair programming is that obviously you've now like got twice as many people working on a problem, and you have to explain everything you were doing to another person, which means I think you slow down massively. But I think the big plus of that is that by forcing you to explain yourself to someone else, like your ideas become much more concrete and your code becomes much higher quality. So I think for like really high stakes code, I think sort of peer programming can be really valuable. I think one thing that I sort of think about when the thing that makes me very resistant to peer programming is that I think like when I am programming, like sometimes I don't even like consciously know what I am doing. Like, just because I do programming so much, there's a bunch of it that like doesn't even kind of get to the level of consciousness in my brain. Like I'm just typing code and I'm like, this seems right. Like, I don't know why, but I can't explain even to myself, but I'm kind of confident that I'm doing the right thing. And so I think that that's the challenge of like forcing you to explain yourself can be like really, really important, and it can be like really, really challenging. But I think the general idea of like, I think one, if data science is programming, then it's really important to look at like what are the techniques that professional programmers, professional software engineers do. Like peer programming is one of them. Like code review is another, where you're not like programming together, but at least someone else is looking through your code and reading it and commenting it before it is committed to anything critical. Unit testing, documentation. I think like if you want to become kind of like a professional data scientist, I think you have to learn some of the skills of a professional software engineer as well. And so sort of deliberately thinking about that and what those skills are, I think is important. I do not know I wish I could like point you to some resource, which is like software engineering for data scientists, but I do not know of anything. Someone should write a book on that.
Yeah, talking about software engineers actually leads a bit into my question, which is just a semantic one, but I mean, you'd like to use this word coding, and I view like programming as the stuff done like by the software engineers, and then you have the natural scientist who cobbles together his analysis using some libraries that he doesn't develop, like SciPy or the stuff in R, and then he's scripting and is then like coding the new scripting, or...
Yeah, I think those are all fine terms. I don't know. I think the important distinction is like being a programmer versus doing programming. And there's something, and I think there's a lot, like particularly when you are introducing people to doing data science. So I think like programming, like when you talk about programming, people have a lot of very strong kind of ideas in their head about what programming means. And if you just simply don't tell people that they're programming, people often like, if you ask them, like, do you know how to program? Do you like programming? They'll be like, no, it's too hard. I don't have the right brain for that. Like, but they can do it. Like if you don't kind of bring it up. So I think that to me is like the important thing, like trying to break these like stereotypes of like what a programmer is, what programming is really important. Another term that some people use is like end user programmer, or end using computing. Like tools that are used by, it's like what do you call the people who are not programmers who do programming? Like end user is kind of one, like normal people is like another, right? Like most people are not professional programmers, and so how do you kind of talk about this? I don't know. But I just really, there's just so many, like people have so many strong beliefs about programming in their head. It's best to try and avoid activating those.
So usually in software development, to kind of tag on to this line of questioning, one of the most critical parts is actually testing, right? Mm-hmm. And it was also mentioned before that, or you mentioned it, that as a programmer, you kind of get an intuition of what you think is correct code while you're typing it, and that kind of sometimes it has this propensity to lead to code that is not actually ever tested or checked, right? And I was just wondering if you had any idea for this like framework of R and RStudio, where you try to get new people also into programming and have non-programmers to kind of enable them to write code that is more easily checked. And also, I mean, if you visualize things, then usually it's pretty hard to check whether that's actually correct, right? It looks good, but maybe it's just not correct.
Yeah, I think that's the hard part of testing like data analysis, is you don't know what the correct answer is. So how do you write a test for that? In some ways, I kind of wonder if like pre-registration is kind of the unit testing of data analysis, where you like say in advance, like you kind of make explicit what your hypotheses are before, then you do the analysis, and then you're like forced to, like you cannot. I think there's some component of this is preventing you from lying to other people, but the most important part is it's very easy to lie to yourself. And just writing down in advance explicitly what you think the answers should be, and then like forcing yourself to confront those differences, I think is really, really valuable. There are some tools, there's like 6 packages in R that allow you to do this. One of them that allow you to kind of express some properties of your data, but this tends to be more useful in kind of the automated context, where you want to say like, if this variable, which used to be a continuous variable, is now a discrete variable, I want to throw a big flashing red arrow to say that the input data has changed. Checking the output of the analysis, I think that's a really, really tough problem.
So what do you think about the R language overall? Like, are you super happy with it to express your ideas and build libraries, or are there things you wish were different, or are you looking to other languages?
I think like overall, like I think R is the thing that like R is just like an incredibly flexible and expressive language, which allows me to write these tools like ggplot2 and dplyr on top of it. And that to me is like the beauty and a small amount of the horror of R. Like the fact that you can like make the language is so incredibly flexible, and it exposes things that basically no other programming language ever would or should, is I think really it feels right to me for data science. The downside of the language being so flexible is that it makes it very hard to optimize, and that means kind of like, you know, by and large, code written in R is slower than code written in other languages. But I basically kind of don't see that as a problem for 2 reasons. Like, first of all, I think mostly the bottleneck when you're doing data science is your brain, like thinking, what should I do next? Or thinking like, what is this data trying to tell me? And then secondly, there is this kind of cop-out way to make R code fast, and that is to write it in C, which is basically the same way that every language becomes fast in the end, with a few exceptions. And so that means, like, for the bits that are slow, that means like it's kind of my job as a package developer to like figure out those bits, rewrite them in a more efficient language so that other people can use them and not have to worry about it. So like R is like far from perfect, but when I look at the other programming languages available today, nothing I think was a better fit for data science.
There's one more question over here, I think.
Thank you. So this is perhaps a bit off topic because it does not concern programming.
But since you are also active in education, perhaps you could share your thoughts and also your experience on this. In Europe, at least, I think my impression is that most data science programs are at the master's degree. What about the States? Are there more programs also at the bachelor's degree? And what is your assessment of this approach? Could you comment on this?
Yeah, so at the master's level, I don't really know how the master's works in Europe. I think it's a little different to the US. But in the US, almost invariably, every master's, if your department runs a master's program, the income from that master's program, which is generally on the order of like $40,000 a year, comes back directly to your department. So there's a strong financial incentive to create master's programs in hot topics. And many departments have, for data science in particular, have kind of taken the cynical approach of data science is statistics plus computer science. So in our data science masters, you will take half existing statistics courses and half existing computer science courses. And I think those programs are like terrible, basically. There are like some that are not cynical and trying to do a good job. At the undergraduate level, I think we're seeing more. There's not many places that offer. I think it's becoming more popular as a undergraduate major, particularly it's sort of or like if it doesn't exist, like the undergraduate statistics major is getting much more popular, and the departments that have strong undergraduate programs in statistics are basically teaching data science these days anyway, just because that is actually, like by and large, what people need is the ability to take data and understand what is going on. They do not need the ability to like prove mathematical stuff about statistics, and they don't need to be able to derive like a t-test or a chi-squared test or whatever, which is kind of traditionally, I think, what you would learn in an undergraduate statistics program. And some people need to know that, but very, very, very few. I think the other change we're seeing is more and more like like psychology departments, for example, like every psychology undergraduate has to take a couple of statistics courses. And I'm seeing more and more departments to switching those to teach R and to focus more on like data science-y stuff. So more on visualization, doing a little bit of programming, and less on this kind of classical, if you have X, you do a t-test. If you have Y, you do a pair t-test. If you have Y and it's not normally distributed, you do a Manhattan-Whitney. Rather than this sort of formulaic kind of tree diagram of statistics, which is not a good representation of what statisticians actually do. It's not generally correct, and it's not like enjoyable for students to learn. They're kind of pivoting to teach data science, which I think is more useful and more fun and just better basically in almost every way.
Thank you.